I wanted to take a quick minute to talk about one of our sponsors that make this podcast possible, and that's Parker Sporlan and the Catch-All Filter Dryer. Do you know what can reduce system efficiencies and reliability within your refrigeration system? If you answered contamination, you are correct. Sporlan Catch-All dryers have been around since 1947 and have been perfected over the years to capture water, acid, solids, debris, including sludges and varnishes. For best practices, change the catch-all filter dryer if any of the following occurs. Initial system install, when a system is open for service or repair, when excessive pressure drop of 5 psi across the filter dryer, when the see all sight glass indicates water is present, when doing a T1-1 acid test kit says there's acid present, during a compressor burnout cleanup, and following a successful burnout cleanup. To find out more information by downloading Bulletin 40-10 from Sporlan.com with all the catch-all filter dryer information. Thanks, guys. Enjoy the episode.
And we're back.
All right, Joe. So earlier we were talking about bullheading in cases and stuff. So I brought up bullheading liquid lines. So What is the proper way once we get that liquid line inside the case to do this? Because I've seen customer A say bullhead. I've seen customer B say don't bullhead. What is the proper way? I would think bullheading the liquid would give you better feed, especially when you're going two different ways. I mean,
absolutely not.
Way?
The best way is to do a true T. You do not want to bullhead into a line because it can create turbulent flow on both sides of that line. And then, like Brett said, you could get bubbles to your TXV and you could starve the evaporator.
We had an instance on a bullseye where basically the case was bullheaded, and you'd see this expansion valve over here start stealing like so much liquid, and then basically this superheat would start getting shitty, and then vice versa. It would just keep fighting each other. We changed the piping, so basically it went through and then came out the bottom, and then went to the nether one and weaseled down next size, and so on and so forth. And the problem went away. We never had an issue with that, with uneven liquid flow anymore.
Yep.
But like you said, there's bigger end users that, that is in their plans where they want you to actually bullhead the liquid line, which never made any sense to me.
No, and it's a standard in our designs.
I mean, that's. Go ahead, Joe.
No, it's a standard in our designs to have notes to stay no bullheading allowed. Yeah, so I don't know. It's good piping practice. You never bullhead. You never reduce. You never go up a size then down a size in terms of either suction or liquid. There's standard piping practices that just are big old no-nos.
Yeah, I mean that's where I'm I guess I was conflicted because I see major manufacturer A doing it this way, major manufacturer B doing it the opposite way. I mean, but yeah, it makes sense. I've always heard no bullheading of suction tees, especially with hot gas, but liquid tees was a lot. Like, I mean, we do a lot of customer A's work, so I was always taught to bullhead liquid tees, but. I mean, I guess that does make sense because of the turbulence to not do it.
Yeah, absolutely.
So since we were talking about suction lines on hot gas, you don't go conventional suction line where you're actually increasing size, as you start adding cases, correct? You keep that header the same distance, so you basically have the same even flow. Is that correct?
That is correct, yes. You don't step down. You don't step up. Yep.
So do you just go off of the, whatever BTUs is going to cover that whole entire suction line? Basically, that's what you go with?
Yes, because you want a full path for that hot gas to travel back. Yep. You don't want to pinch that. You do not want to create a restriction for that hot gas because that's going to increase the amount of time it takes to defrost the case. You're going to get your most efficient hot gas defrost when you have a full path of flow through to that evaporator.
I've done this already where like I tried manipulating, like even though you're not supposed to drop down the sizes, I had on hot gas systems where, basically I was getting a system that was, getting the brunt of the hot gas just because of the way that, that it was piped. It was 96 feet of basically coffin case.
Okay.
And I've never seen that much case on one system. So basically wherever, it was piped in where, it would go right to the ends and, the end caps, and that's where it would defrost first. So the only thing that I did to help combat that is basically drop it down one size from the main header. So then that way it was restricting the flow a little bit more. So you were less likely to get, full on flow going to those particular cases at the end of the line.
Right. Well, first of all, the first thing that's wrong about what you said is I would never put any more than 3 cases on a given circuit. It just causes problems inherently. When you send that 196-foot case into defrost, what happens to the rack?
It starts eating shit because it's more than 5% of the whole load.
Yep, exactly. We have hard and fast rules in our office that we will never put more than 4 cases on a circuit unless it's a doored case, a doored medium temp case. Then we'll go for 6.
What's the reasoning?
The loads on medium temp doored cases are like next to nothing.
Oh, right.
Yeah.
Usually for a medium temp case, it's usually like, I don't know, anywhere from 13 to 1500 BTUs per foot. And it literally doesn't go down to like 300 BTUs per foot when you get down that when you put the door cases on there, when you put doors on the cases. Yeah.
Absolutely. Yes. I'm actually in the middle of doing a design right now with a client that's doing all doors all over their supermarket. They are not sparing anything, not even fresh meat. And my loads on my racks are next to nothing.
All right. So
now that we just opened up this door rabbit hole, can we kind of talk about what happens, explain to people when we start throwing doors all willy-nilly on cases? Because I've seen this go 2 ways. I've seen it where they've resized all the piping and done double risers and everything is okay. And then I've seen it where they just slapped some doors on there and said, choke the valves down and hopefully we don't grow mold and it doesn't wipe out the rack. And obviously, number 2, disaster every time.
Yeah, absolutely. I'm glad this kind of came up. Like when you add doors on an open case, you absolutely must check the line sets because more than likely they're going to be oversized. Yes.
How does that affect the TD? That was the question that was burning. As soon as you guys started talking about this, I'm like, well, wait a minute. Like now that the case isn't basically open, there's going to be no change between really return on supplier. So what does that really do to your TD as well?
It drops it down. It drops it down to next to nothing. Now your TXV is oversized, right?
Yeah.
So now the TXV has to be pinched down in order to maintain the same superheat it had before.
Correct.
You've lost your mass flow as soon as you do that also. So your mass flows reduced dramatically.
Yes.
So then you'd have to do double risers to make sure you do get the oil returned back. Otherwise, you're going to have evaporators just sitting there with a shit ton of oil in them.
And then you're going to have case alarms because now they're not cooling. Yep.
And then on top of it, you might potentially have a problem with your separator as well if it's basically like a turboshed because they're CFM based. And the fact that we basically dropped our load down from probably like a tenth of the case load that it originally was, that's going to translate to compressor barely running. So, you could potentially have the problem that we talked about before, where basically then those type of oil separators then become oversized, and then you don't have shit for oil separation as well. Yeah.
Absolutely, absolutely. And it just exacerbates the issue. Yes, yes. So
Yeah,
really,
I've take risers from 1.1 down to 1/2 inch on some.
It is that drastic. It really is. Yeah.
And then we have one customer up here that decided that they weren't doing any of that, and that the racks were already maxed out, so it wasn't going to be a problem until it was a problem, and then it was a problem. Soon as summertime was great. I mean, we had heavy head pressure problems. I mean, it somewhat had oil return. We hit wintertime, and that's when it wasn't great anymore.
It just crashed. Yeah. Yep.
Yeah.
Nobody thinks. Nobody thinks about the winter months when they're talking about refrigeration because it's already cold outside, right? Like, no, that's not the way it works. You have to think about the winter months when you're loading up a rack. Like, you have to have an even mixture of open and closed load on that rack. Because really, if you think about it, especially if you have a loop, if you don't have a mixed amount of load on a rack, your doors are going to shut off more often than your open cases are. And then that's going to reduce the mass flow requirement in your main loops. And now they're going to become oversized. And they're going to starve all the cases that were operating correctly before those other cases dropped off.
Since we keep going down more and more rabbit holes, what's going to happen to for energy? Like you guys do energy design.
Yeah.
Have you guys ever quoted a customer to basically do a lower RPM motor to get more of a TD out of the evaporators?
We actually, usually as part of a door implementation, we specify new ECM motors to go in the case, 2-speed ECM motors.
Mm-hmm.
And the reason we do that is because we don't require as many air changes in the case anymore because it's a closed environment. So we can actually slow that fan down.
So Kevin, you've changed sizes, you've changed speeds on the MPAS motors, right? The ones that come in the Hill Phoenix cases, yeah.
Yeah, so with the programming stick, the shocks lose the shit out of you if you don't power.
if you don't read the freaking directions. So they have this.
Yeah, which that the first time.
So on the stick, there's a big ass tag that's attached to it. But I'm a guy, I don't read directions. So it says really, really big, do not have the fan motor plugged in while you're actually changing the speed. Kevin and I must be a lot alike because, basically we both didn't read the fucking directions. And so, because we're both telling the story. It's like, yeah, that happened to me too. Kevin, do you know what the purpose is of having two speeds on there? Because there's a speed 1 and a speed 2, but there's no selector, there's no third leg to basically tell it when it's supposed to be running the speed. Do you know actually, because I'm asking because I don't know, do you know what that's actually for? Like why they actually have two speeds on there?
Assuming there probably is a third leg, in that plug, and they probably just don't pay for it, so they probably don't use it. Like those motors are way more prevalent in Europe.
Is this on a tub case or a door case?
Either.
It's on all, like Phoenix, and our junk, even some Husband stuff. They all have these even PAPS programmable motors on there, so you could change. They're basically making it like a universal motor. So they stock one motor now and maybe like 2 different blades, and they can change whatever they need to for the fan speed.
So
and sometimes it doesn't ever.
So I will bring up a point. When you have a tub case, like a coffin case, they'll usually have multi-speed motors in those cases because if you put lids on, you need a lower fan speed. And that's part of, they not only change the fan pitch in the case, but they change the fan speed as well.
Well, no, these are the ones where they're basically they're the blade and the motor. I mean, everything is plastic on it, so there's no changing any blades on these.
Okay. Okay. Interesting. Then I guess
But like
maybe
I said,
it's like just a universal motor, right?
yeah, and then you can just basically change out the just plug in this stick with the power not on, and then basically program it to where you need it to be.
Yep. Yep.
Looks
So,
like I'm going to be.
Joe, now when you guys are and you're putting 2-speed motors in, so are you guys putting in 2-speed ECM motors, or are you just putting standard mode ECM motors in? Because I've seen it both ways. In the 2-speed motors, what are they doing? Are they, when the case makes temp, are they dropping to the low speed, kind of like all the new evaporator coils?
That's exactly right.
Or okay.
Yeah. Yeah. So yeah, you know that the Department of Energy now has requirements for all walk-in evaporators to have 2-speed motors to meet efficiency standards for DOE. Then they're just doing it with a simple relay, basically. In the cases, we do the same thing, basically. When the control system determines that case has hit temperature, it'll slow the fan motor down instead of turning the refrigeration off. And then it waits a certain amount of time, and then it turns the refrigeration off. It keeps refrigeration going.
I mean, that seems from a control standpoint like almost like a nightmare. I mean, especially from a troubleshooting standpoint. I mean, that seems like a 2-speed motor setup instead of a case seems like a nightmare for superheat control and everything else. I mean, especially if you're using steppers to control something. I mean, that seems like that could really throw some guys through a loop. I mean, I wonder what the cost benefit to, actual breakdown benefit would be. I mean, it seems like it would cause more problems than it would save for energy.
True.
Yeah, because on the two-speed motors that you're speaking of, they usually hook up. There's like a third leg on those motors where basically they can tell it to go to the other speed, and basically what they do is they use the other line coming like off, because usually they put an A19 right on the evaporator itself, and then basically when it switches the power from the normally closed to the normally open, then that powers the other part, and then that's when it ends up slowing the damn thing down.
Yep, exactly. That is exactly how they work. Yep.
All right, keep grilling them. We're gonna break them. What else we got for them?
Go ahead, you can try. I've been doing this for 19 years.
So, trying to think. Well, we go over condenser sizing, like actually,
yeah, sure.
Why we got them on here? How to actually size a condenser? Because I know I get this question a lot.
Yeah.
Okay, Joe. So how would you go about sizing a condenser or checking a condenser size? I get that question a lot. Is this condenser size big enough for this rack, or is it just that nobody's cleaned it properly in 10 years?
Okay, so it's actually a pretty straightforward method to sizing a condenser. I mean, the first thing you need to establish is what is the total THR of your compressor rack. Of compressors that are actually operable. If there's valved off compressors, I don't include them in my calculation. Then I get the condenser model number. I look up in the literature what the rated value of that is of that. But even before that, if I'm evaluating existing condition, I need to know what the TD was that it was designed to, whether it was 10 or 15 degrees or even 20 degrees. Once I know that value, then I can get the condenser capacity. Then I can compare that to the compressor TD or compressor THR, and I can figure out what the total TD of that condenser is versus design. As long as I'm underneath, so for example, when we size condensers for a system, if we're sizing for a 10-degree TD design, we'll always size for 7 to 8 degrees actual. If we're sizing for 15 degrees, we'll go 12 to 13. You build a little bit of spare into there because that a couple years down line, that condenser is going to get dirty. Something's, you don't know if there's cottonwood in the area or something like that. So you need that extra spare in there to accommodate that.
Is that why the TD increases usually when you have a lower ambient a little bit? Just because then basically, because engineers size in that extra little bit.
Yes, absolutely. Yep.
So with that being said, like when you guys are actually sizing, the actual condensers for the ASHRAE temperature for whatever area, and say Chicago's like 110. Are you guys oversizing that also? Like I've been seeing like engineers kind of fluff that number a little bit too. It looks like, the lab racks I started, we've been 115.
So general practice is we go in our office. In the past we have gone in 5-degree increments over ASHRAE 0.4% data. Now we're going in 1-degree increments. We no longer, since we're building spare into the condenser with our sizing, we no longer build spare into the actual temperature that we're defining our TD off of, because that's spare on top of spare, right?
Yeah, it makes sense.
Yeah. Now, I can't speak to what other engineers are doing. I don't really pay attention to what they're doing. I keep my head down and I do what I do.
No, it's great to see how other people do things. I think seeing how like you're explaining it and how I've seen other people do it. It's good to see like different sides of it. Definitely. The piping thing's been a huge training thing right now, especially with you going through line sizing and stuff.
All right. If you got the answer that you got, I got some questions now.
Yep, go ahead, Brett.
So on a rack that I was looking at under system summaries, this is a bullseye. Basically, it had total load BTU per hour.
Yep.
And then it had non-subcooled capacity BTU per hour.
Yep.
And then it had subcool capacity BTU per hour.
Mm-hmm.
And then non-subcooled safety factor. Okay. So BTU load, I'm assuming that's that's
the load on the rack.
Okay. So then what's the non-subcooled capacity? Because I'm seeing one number of 559,175, and then not non-subcooled capacity goes up to 625,000.
Yeah, so what that is that's that non-subcooled capacity. That's telling you what the compressors can handle without any subcooling on the rack. So let's say the subcooler breaks down, there's still spare capacity built into those compressors.
Oh, okay. So all right. So basically, okay. So total BTU load that's just everything that's on the cases, and then non-subcooled capacity load is basically just all the capacity of every single compressor rolling on there, right?
Correct. You're assuming a full run, and that's the full capacity of the rack. Yes.
Okay. All right. And then
now that brings up one good point that I just want to interject.
Yeah.
When you're sizing a condenser, you never, ever, ever use subcooled capacity of a compressor, because the subcooler comes after the condenser.
Okay. And then what the hell? Oh, okay. Never mind. I think I just answered my question now that I know the other two numbers. So non-subcooled safety factor is basically how much more capacity you have versus the full load versus the compressor load. Is that correct?
Is that in percentage?
Yes.
Yes. So that is the spare percentage of that rack, basically.
You got the fucking Rain Man of engineering. You knew that there was a percentage. All right. And then basically we have the other number, which is subcooled capacity BTU per hour, but that's only on one rack. I'm assuming that's what that looks like is basically the amount of percentage that the compressors increase. So typically you get anywhere from 27 to 30% capacity increase when you go from a standard number like 100 to 50, right?
Correct.
And that's why you can use, basically when you subcool liquid, you also can technically you can undersize your equipment. If you're fully relying on that subcooler, hence why when a subcooler isn't working, one of the things that you'll see is that the rack will have a real hard time maintaining suction pressure because now the compressor BTUs isn't big enough to actually hold out the load that's actually on the rack itself.
Absolutely.
Yes?
Everything.
Hey guys, I want to take a break and talk about Westermeyer, one of our other sponsors. Today's episode is sponsored by Westermeyer Industries, the leader in oil management and pressure vessels for the commercial refrigeration industry. Repairing refrigeration lighting can be performed quickly and profitably by utilizing the Luminosity Kensington Refrigeration LED. Kensington was developed by the supermarket refrigeration community to be a near universal solution for refrigeration lighting repairs. At Luminosity, we saw the frustration of technicians making multiple trips to the store sites to determine the correct parts. Labor pileups, dispatch remains open for months, high prices for the replacement parts by the OEM, and customers refusing to pay for all this effort, leading to unbillable or end-of-life invoices. Our goal was to develop the Swiss Army knife LED that technicians can carry on their trucks or at their shops to provide a one-and-done lighting repairs at a profit. Once your customers experience the clean, bright Kensington LED, they will be asking for more and making you more profits. The Kensington LED features secure metal mounting bracket for an internal driver, near universal solution for reach-in doors and air cases, walk-in and prep rooms, one-and-done repairs, easy and labor efficient to install. They have a built-in LED driver that has a universal 120 to 277 volt input, easy and secure mounting, HVAC and refrigeration contractors in the United States. They're made for damp locations, rated IP44. They have a 7-year warranty, available in 4, 5, and 6 foot lengths, and they're tested in all major brands of refrigeration units. They're also utilized by most of the major. For information and pricing, please contact Pete Murata at Luminosity. His email is Pete, P-E-T-E, at i-luminosity.com. His cell phone number is 209-814-8129. Check out Kensington Refrigeration LED and our full line of quality products at www.iluminosity.com. That's www.i-luminosity.com. Thanks for listening, guys.
Thing you just said is 100% correct. Yep.
Yeah, smart.
We don't actually include, when we do our designs, we do not size our compressors to take advantage of subcooling. So we don't undersize our compressors. We size our compressors to roughly 0% spare, and then we let the subcooling handle our spare percentage. It's almost like a happy medium. You don't have to have spare compressor capacity because you have subcooling, but if your subcooler breaks, you'll be okay. On a non-design
that
day.
Seems like a better alternative. Yeah, it seems like a better alternative than, relying on the subcooler, and next thing you know, everything's broke.
Okay, well, so that brings up another point, because sometimes you have, you stated before, which, we went over on the podcast before, when you subcool liquid, because basically the refrigerant now has more capacity because it's denser. It basically has more mass, less volume, right? So it takes up less space.
Sure.
So basically, that's why we can go, downwards on the pipe.
Mm-hmm.
So there's no safety net in that. So basically, you're kind of shut up the creek, because like at that point, you would be potentially having flash gas all over the place, because basically your expansion valves would probably exceed the amount of BTUs in the pipe at that point, because that refrigerant is not subcooled. Would that be an accurate assumption?
It depends on if you're in a design day or not. If you're in an off-season day, like fall, spring, winter, you might not have a problem. If you're in the dead of summer, yeah, you're kind of going to be up the creek without a paddle.
Yeah, because I've seen it.
Sorry. You're good. Your system's basically just gonna go like this.
Yeah, because I've seen random cases like just when you do have an issue, you'll see random cases will basically start this one will start running a little high. This loop, the farthest down that one that'll start running a little high, in the middle of summer because basically now you don't have that subcooled liquid, the larger capacity.
Yep.
And the pipe's not really big enough. Like you said, you could potentially going from 100 degree down to down to 50 degree, you could decrease that pipe size from like 7/8 all the way down to 5/8. So then you randomly have cases, running a little higher because they're running the higher superheat. Go ahead.
Well, not even that. A lot of case manufacturers will look at an engineered legend and see that subcooling has been applied, and they'll size the TXVs for that subcooled liquid temperature.
Yeah.
So that'll be affected as well.
Yeah. That's,
in a lot more coils, not so much cases anymore. Like I've seen them kind of back off in the sizing for the subcooler. But most of the time it's been the walk-in coils. They've been dramatically undersizing the valves.
Same thing with the nozzles. Like when you subcool liquid, you actually require a smaller nozzle.
Correct.
Because then if you don't have that smaller nozzle, you don't have the right delta across that actual distributor.
Yep.
And then what I've seen is you basically get what I refer to as lazy liquid feed. Or basically your liquid coming out of your distributor has a clap where it just drops to the bottom, and then basically you'll get uneven liquid feed, right? And then basically you'll basically on the coil you'll see a triangle. You'll see lots of frosty from the start all the way at the bottom, all the way to the suction, and then you'll see a little bit less on the next run up, a little bit less on the next run up, and the first U-bend might be frosted just that little tiny bit. And then that's it. And then basically you could draw a triangle where, you don't have enough liquid feeding, going across that whole distributor.
Yeah, because it's not moving fast enough and it's not going through the whole coil. It's absorbing all the heat before it passes through the coil.
Oh, I know what we're doing in the next podcast. Joe's coming back and we're going to talk about distributor sizing because that's something else that just eludes me.
Yeah,
it's all about pressure drop, baby.
That's I've yet to get down and get a hard answer on nozzle sizing and like distributor sizing.
Yo, I have a tool for that too. I can bring it up on the screen.
See, that's nice because I've gotten so many different answers depending on who you talk to at Sporlan about nozzle sizing or who you talk to at Heatcraft. It almost seems like sometimes some of these coil manufacturers are just guessing.
Really, honestly, it's to be just. I'm not talking about this anymore, but it's based on tonnage, just like TXVs. It's based on tonnage, but it's a little more involved. It's a little more involved than a TXV selection because there's a whole bunch of thermodynamics involved. But we can definitely cover that.
Sweet. All right. What else was on your list? You were jumping around, man.
Well, I covered how subcooling affects liquid. Let me see what else I had on here. Hold on.
Oh, UV jacketing. Talk about that a little.
Yeah, so this is something that is near and dear to my heart, and it's something that I've found lack of evidence of on a lot of installations that I've gone to. UV jacketing is an absolute requirement when you're running refrigerant piping outside. Things like birds, the sun, the wind, life, people, anything that comes in contact with that pipe will deteriorate that insulation. So UV jacketing is 100% a no-brainer. And I'm not talking UV paint is okay, but it's not the end all be all. You have to jacket your pipes. You can use the plastic. I prefer the metal jackets, but you've got to do something to protect your insulation when you're outside because it won't last 2 years. It will not last 2 years. And then the next thing you know, you have bare suction lines and you've got problems with your system because you're getting way too much superheat built into your lines from the sun.
That's just when you start subcooling it down to like 10 degrees. So by the time it gets to the case, you were still at 50, right?
Right, exactly. Band-aid the system.
Yeah, I've been seeing a lot more, like, especially new stores where they've started increasing the suction line insulation. Like the last couple have been like 2-inch, even on the medium temp, and on the low temp it's been 2.5-inch Armo. I'm assuming the reason. Go ahead, Joe.
No. I'm just responding to your point. Like, so you're seeing an increase in insulation size on roof-mounted piping?
On store-mounted piping.
Store-mounted piping. Okay. So what a lot of end users are really concerned about right now is energy spend. They're really, really highly focused on energy spend, and it's really not that expensive to spec a thicker insulation. That's one of the more low-hanging fruit things of a refrigeration install, because you've got to put insulation in anyway. So if you go another half-inch bigger, it's going to save you the energy. It's almost like a no-brainer. There's no ROI to it, you know.
Except for right now, when Armaflex is almost as much as pipe.
Well, true. But yeah, but we all know that right now is ridiculous.
Like we had a store where they bumped it up from it was 2-inch to 2.5. It was a $50,000 increase.
Wow, holy cow!
Literally, Armaflex right now is more than pipe. Like, it costs more to insulate a 7/8 section of a 20-foot 7/8 line of ACR than it does to buy the pipe.
Holy crap!
We're gonna start having dry.
I couldn't believe it. I mean, at the end of every job, we're tossing insulation in the dumpster 90% of the time because the shop doesn't want to deal with it, because the wholesaler won't take it back, and there's already $97 Armaflex at the shop, and right now it's worth more than the pipe. The crackheads are going to start. They're going to start scrapping the insulation here pretty soon.
Yeah, they're going to start ripping plywood off of buildings, seriously, because that's a premium as well.
Oh, yeah. I was on a new warehouse build the other day, and all the walk-in panels came with plywood around, and there was people out there fighting over it. It was all stacked in a pile, and there was literally guys out there arguing over it, because usually it ends up in the dumpster.
But it's really funny. Just to speak to that point, I was talking about plywood today with a client. Where was he? He was in, I think it was California, and he said to me, what used to cost a sheet of plywood that used to cost $16 is now $60 out here. I was like, what? Okay, we've hit prime time here. Seriously.
They're not going to be ripping out the copper pipes in a house anymore. They're just going to be ripping off the freaking piece of plywood on the outside.
Exactly.
You got some of that plywood? You got some of that plywood?
So, Joe, to speak to that savings on that Armaflex, is that just from the keeping that suction line temp coming back at that colder suction temp is obviously more. Suction line gas is more dense, and more dense gas is obviously easier and more efficient to pump. So is that where the savings comes in?
Absolutely. You reduce the amount of heat gain into the system. You make the compressors work less.
Yeah, it makes sense.
Yep.
Well, maybe this is a dumb question. Well, all right, let's just assume that the store is always at 75 degrees Fahrenheit and 55% relative humidity. If you had, how much more or less drop are you going to have by just increasing that insulation size by a half-inch?
You could see usually you can see about a 5 to 6 degree decrease.
Really, just in a half-inch insulation?
Absolutely. Well, it depends on the run, but yes, absolutely.
So then that's going to cause lower discharge temperatures and lower maintenance costs, because the compressor is going to be running a lot cooler, right?
And less compressor energy, so less on your utility bill.
Yeah, well, your BTUs increase too as well when you actually lower your suction line temperature. Yeah.
No, because think about it. Your compressors will run more when you have a heat add on the suction line, right? Because now your suction pressure is elevated coming back.
Yeah, you're essentially turning the suction line into an evaporator. You're picking up more heat.
Basically.
Okay.
Basically. Yeah. It's an evaporator after the evaporator.
Okay.
Yeah. Yeah.
Oh, that makes sense.
In a perfect world, you wouldn't lose any heat but in the heat source, in the heat sink, right? Like, and you wouldn't release any heat but in the condenser up on a roof. In a perfect world.
All right. You wanna touch on underground piping?
Yeah. Okay, so the one point that I want to make about underground piping is it's got to be properly encased. I'm not a big fan of sweeps, PVC sweeps. It doesn't permit for service. It doesn't permit for traps. It doesn't permit for proper piping installation. I prefer either a pre-manufactured or a concrete poured box at either end. Well, usually what I like to specify is a drain in the bottom of that pit box so that it can actually naturally drain instead of filling up with water and dead mice and things of that nature.
Well, no, you want it to fill up like that way because then that way it makes finding leaks a lot easier, right? If it's filled all the way to the top, you'll see the bubbles and you know you got a leak, right?
Yeah, exactly. I prefer overhead piping to underground.
It must be more of like a regional thing. I mean, because we never see pit boxes out here. I mean, I could think of maybe like 2 times in the last 7 years I've seen pit boxes out here on new startups. Everything's been buried PVC.
Really?
Kevin, where are you out of?
Chicago.
Okay.
Yeah, I hardly ever. I mean, every once in a while we'll see like some smaller pit boxes, but I mean, just about everything's been buried PVC, and then the trap's obviously done in like a small pit box, but like we hardly ever see like 3x3 pit boxes like where you could actually serviceably pull pipe through. I mean, they just don't do it. I don't know if it's because of the frost pattern in the grounds and stuff, or if it's more of like or if it's just like the customers we have out here.
I mean, it does present kind of a maintenance issue because it allows, just like Brett just talked about, it allows for a place for rodents and condensation and things to hang out, basically. And again, all those things can deteriorate insulation. You're not going to jacket your insulation underground because you don't need to. So, but what we usually specify is the Craig boxes, the pre-manufactured boxes, the plastic ones.
Yeah.
I like those. They tend to be pretty impervious. And if the contractor who's installing the job seals the PVC around where he drilled the hole, you get a pretty good installation, and you don't usually have that issue. So
I had a GC up in New England that didn't know how to use a tape measure.
Mm-hmm.
So basically, it was supposed to be a straight 30-foot shot from box to box, because usually those boxes are like 4 foot deep.
Yeah.
I think 2 feet by 2 feet, and then you just basically cut out a hole, where it's going into. You know what I mean? Where you lay the PVC jacketing in there, whatever. And so we, and it was. I think that it was supposed to be 10-inch PVC, and because, I guess when they were doing the plans, they didn't realize that the floor was like basically really, really reinforced, rebar and everything all over the place. So they were going through diamond blades like crazy.
So it was a post-tension slab, yeah.
So anyway, at one point he's just like, that's deep enough. I'm like, well, it calls for 10-inch. He's like, just put 6-inch in. So we basically had 4 line sets going into a 6-inch piece of PVC.
Wow.
We used a lot of Dawn dish detergent to slide everything in, because not only was it, tight already, but because he didn't know how to use a tape measure, we had to end up using a couple 45s to get it where it needed to be.
Mm-hmm.
Not a fun time. Not at all.
Sounds to me like the conduit wasn't sized properly for the amount of pipes that were going through it.
Well, it was, like I said, it was supposed to be 10.
Yeah.
But he didn't want to dig any deeper because we were already behind. The concrete truck was coming. Oh, it's coming in an hour.
Oh,
okay.
gotcha.
Yeah.
Gotcha.
So get it done as quick as possible.
So the other thing I'll say about underground is I never let my runs from box to box exceed 20 feet, because that allows me to size hard pipe if I need to accomplish my load. Let's say I have a supermarket retailer that wants everything underground. If I run into a situation like that, do not size your boxes any further than 20 feet from each other in case you need to use 2-in-1 or bigger.
Have you ever seen 2-in-1 underground?
With certain clients, I actually have, yes.
I see up here, like I think in the last 5 years, maybe like 1 or 2 underground runs at some random stores. Like almost everything here has been overhead. Even that big box store that likes the bullhead tees has been dropping down everything in PVC columns, which I think is a lot better option. I mean, me personally, I can't stand underground. It's an absolute nightmare.
I would agree with you as an engineer from a service standpoint. It is absolutely hard. Seriously, it's horrid. We try to run overhead wherever we can. We actually just developed a prototype for one of our clients, and we're only running underground, I think 4 times in the whole entire store, and it's only to like a salad bar, coffin cases. It's the bare minimum, like. I'm not a huge fan of underground anymore, but if a client requests it, you gotta do what the client asks, right?
Yeah, obviously, yeah. I mean,
Yeah.
It's just it seems like it's going away more and more. Just as all these refrigerant regulations come down because it's just not serviceable.
Yeah,
but yeah,
it's not serviceable. You can't get to the leak if the leak develops. You disrupt the store more so than you would have with overhead piping. It's just not a good situation. Seriously.
So it's a couple more years from now. I'm 15 years from now. They're going to stop putting in racks, and everything's going to be case controllers and propane cases.
Self-contained, water-cooled. Yep.
That's going horrible. So I don't care what they say. That's 10 times the amount of service calls, and yeah.
Well, you got a lot more years in the field to go because you're like 20, right?
Well, you're like 50, and I'm 1.
Oh Lord.
Horrible.
I mean, if I make it to 50,
I'm broken and everything, and then I'm dying.
I'm like 50 right now.
All right, what else we got? You got anything else to? I feel like my head's gonna explode.
Sorry.
Yeah, I'm pretty wiped out. I actually learned a lot doing this. So I mean, I really appreciate you coming on here, Joe, and taking some time and going through some of this stuff.
Dude, I have more. Anytime you want to have me back on, I have more.
Yeah, I would love to do like an actual like piping layout. Like if we could draw it out in cases and get some pictures. And I mean, I see this a lot as I'm doing commissioning. I see improperly piped cases, and I mean, especially as we're trying to get these installers where they need to be. I mean, it seems like a great learning experience for a lot of people.
Yeah, absolutely.
Let's figure out how to make some clear piping. And then we could basically somehow weld the clear piping in, bullhead it, and see what happens in the lines. Because I'm really curious, like what it's actually looking like actually inside the pipe. You know what I mean?
Like where the bubbles form and so on and so forth.
Now you get all that free time, Brett. That's plenty of Brett free time.
Free time, shut up. Work smarter, not harder. Once you're done with your Fisher Price My First Bag, then maybe you'll work a little bit smarter. Jerk.
Well, guys, I think this is a good place to wrap it up. I really appreciate you coming on, Joe. I mean, this is a great learning experience, especially for me. I know Brett probably learned a few things, maybe. But have a nice night. I really appreciate it.
Yeah,
right,
you guys do too.
Thanks, Joe.
Bye.